Okay, so I hope that you all were able to navigate to the repository. Yes, all the tutorial can be followed just by reading the README. There are exact steps, and also by the end of each step there is sort of a finished solution that you can just copy to your directory and run if you do not wish or if you got stuck in some of each step. If you want, you can go through it by yourself in your own pace, but I will just go through it slowly with you. And yeah, if you have any questions, just let me know and I will come to you and try to solve the problem with you. I will be visiting many topics. I think that, well, I could start by showing you the whole simulation at first, but I think that what could be more educational that you would try each and every time step to simulate by yourself. And that's how we will go with this tutorial. Yeah, we will use the PhysiCell Studio to tune your simulation and also to visually see how the simulation goes. But in order to have that, we need to have download some dependencies. So I would like you to go with the first step of the setup instructions. That is just cloning this repository to your folder, going to that directory and fetching the submodules that will be required. Here are the general requirements that you need. You need Python, you need make, you need Git, and some C++ compiler. I think that this could not do. This is not a problem. I hope that many of your systems have it. Is anybody on Windows here? Okay, for Windows, you need some Linux-like environment. So if you have Windows subsystem for Linux or MinGUI, well, I can assist you. Okay, so maybe I can follow along. Yeah, so the cloning takes some time. And when you finished that, you can create your Python environment and then source to it, which is the second step here. For that, you need to have a Python virtual environment module. So if you do not have it, just install it like this. Yeah, so now you can install the requirements so that you can open Python, so you can open Studio. Yeah, and I used a wrong Python version, so let me just do it again. Python 3.11 at least. Sorry? Maybe. If you go through this step of installing requirements, then it will work. Okay, does anybody so far need some assistance? In the meantime, while we are unstacking people using the interactive Fugaku session, is there anybody who has finished this step? I'm scroll down. Okay, so Eventually, in one point in tutorial, we will need to open a graphical window. So perhaps this is another issue that we will have in Fugaku interactive session, that you need also graphical session. So we are just figuring it right now, how to do it. Maybe I can suggest just to run it from your own personal computer. If you have a Linux-based system with enough, that will be completely fine. For the rest of the people, the solution is coming soon. So let me just continue with the tutorial, yeah? And yeah, then we will go back. So what is next here? Yes, so let's start with the diffusion time step. So before we open the PhysiCell Studio, which is the graphical tool that lets you set up the simulation, we first need to compile PhysiCell. And to compile PhysiCell, you need to do these steps. So you need to cd to the PhysiCell repository. Then you need to make template which configures the C++ template project, and then you need to just build that project. So let's do that. So when you cd to PhysiCell, when you write make template, it should look something like this. And then when you do make -j, it should compile. And when you see this executable name is project, then you successfully arrive to the compiled binary PhysiCell. Great. Now we can finally open the PhysiCell Studio. So let's just copy this command, which will open the studio with the compiled project and with the configuration file. This PhysiCell _settings.xml is the configuration file that contains all the required parameters for us to run the simulation. Okay, so maybe just pay attention to the tutorial that I will do right now. So I just can showcase to you how to use PhysiCell Studio. So here you can configure the domain. So how big the domain is. It is in microns. So here we have just 2D domain of 1000 times 1000 microns. And what we will do now is that we will put the simulation, the save time to much smaller number, something like 0.1. Yes. And we will set the max time to just 100 simulated minutes. Yes, this will help us to observe the diffusion scale in a better detail. And now we can actually go to the Run tab and just run the simulation. And you can see that it finished quite quickly in 2 seconds. And when we go to plot, there are some cells already here, which we will ignore for now. But what we can click is we can tick this substrates box, which will actually show us the actual substrates that we have in our environment. There is some default value for the substrate, which is 0. And as we run the simulation, we can see that, well, nothing is really happening. So what we can do now is that we can actually alter the microenvironment. And by that I mean we will add some boundary condition to the domain. And by that I mean that on some side we will say that this side will be outputting the substrate with some rate. Let's put 1000 there. And let's put on. When we do that, let me just check if it is 1000. Yes, yes, yes. Then we can rerun the simulation again. And now we can see that something is actually happening here. left side, where we set up the Dirichlet condition, we can see that some substrate is propagating through the domain. So with the maximum concentration of 1000 and decreasing as you move on through the domain to the right. Okay. What do we have next here? Okay, so now we can actually play with the diffusion parameters. So we can actually decrease the diffusion coefficient quite substantially and also decrease the decay rate, which will let us to see that the substrate will diffuse much more slowly. We will observe it diffuse slowly. And since I decrease the decay rate, we will also see that it will be able to propagate further in the domain. Yeah? So if I were to keep this simulation running for some time, we would eventually see that the whole domain will be filled with the substrate. Yeah, and then what we can do is also we can introduce a new substrate by going to Microenvironment tab, and we click New. And here we can set up the new parameters here. Let me put just something there. Here I'm setting the Dirichlet boundaries for each side of the simulation. And in the plot, I can actually check a different substrate and see how that propagates in the space. Yeah, it is here. So here I can see which substrate to display. Great. So this by itself is quite boring. So what we can do, we can actually set cells to secrete or uptake the substrate. So in order to do that, we first of all need to enable cell configuration of files, so we can actually place cells in the simulation. And now we can put the cells inside our domain. The simplest thing how to do it is to go to the IC tab, and here we can plot the cells however we want. Here I will go with the default, so I will create some disk of 100 cells with some diameter. So if I play plot here, some cells will be put into the environment. I will save it. And if I run it now, hopefully the cells will be there. Yeah. So if I go here, I can see that cells are here and they are living there. Great. What we can do now is go to the cell types tab, and here we can change the secretion tab here. So we can change how these cells will either secrete or uptake specified substrate. Let me check which parameters to set here. Okay, so we put secretion rate to 100 and target to 5000. So this means that these cells will secrete with 100 substrate values per minute, and they will try to reach the target of 5000 density of the substrate. Yeah, so now that I'm running it, you can see that when I tick the substrate tab, you can actually see that we are observing that the cells are indeed extracting some, secreting some substrate into the environment. Well, next we can actually modify the uptake or secrete rate of the cell for a different substrate. And here we can actually write something like this here. When we run it, we will see that the cell will be secreting one substrate, but uptaking another one. Yeah, here you can see maybe in these parts that we have some lighter parts here because the cell is uptaking the substrate here. Okay, I think I will skip this advanced example. In this example, I just wanted to show that sometimes maybe having cells as sources, as sinks is not adequate for you, and maybe you want complex regions of the domain to do some secretion or uptake, for example, to simulating some veins in the environment. And for that, you can actually define a so-called bulk sources or bulk sinks, where you can specify specific voxels to do the secretion or uptake. Yeah, so let me skip that. And the next step is the cell mechanics. So in this example, I increased the save data time interval to 60 minutes because the mechanics steps happens less frequently as the diffusion. And yeah, I added some more cells to the simulation, and I let it run for some while. And here you can see that the cells are going through division, but the most important part to note here right now is how the cells actually can, they occupy the space, not overlapping themselves too much. But you can change this behavior however you want. For example, you decrease the cell-cell repulsion strength by 1 magnitude in the mechanics tab of the cell type. And then when you run the same thing once again, we will observe that the cells will overlap a little bit due to the shear pressure of the simulated number of cells. Yeah, the cells are overlapping much more here. The next thing we can do, we can actually give some logic to the cell through the motility tab. And here we can enable the motility so that a cell would by itself move either towards or against the specified substrate. So here I enable the chemotaxic motility. And if I run it once again, then here you see that the cells are very quickly coming towards the left wall, which if we also tick the substrate, you would see that the substrate is here. So they are just following the substrate gradient to follow, yeah, where to go. Okay. Maybe now I will skip a few steps here. The step that I skipped here is the springs. So here you can set the attachment and detachment rate in the mechanics tab to some value. And in this case, in a probabilistic manner, a cell can attach to another cell and drag it towards its motion. So you can experiment with that yourself. But what I will show is the whole example of a prepared solution that or prepared simulation that is here that I think will be quite interesting. So let me close the window now and rebuild the PhysiCell for the biorobots project. Yeah, so here I am just cleaning the current project and making the new biorobots one that is prepared in the PhysiCell repository. And now I can just open this project with this command. So I just open the PhysiCell Studio once again, but pointing to the biorobots project. I will let this simulation run. And here we will actually see the all the different steps in the play. So maybe pay attention to this simulation now, because this actually shows the power that you can do with PhysiCell. Yeah, let's wait a few more seconds for the simulation to finish. It is running on my local laptop. Thankfully, it is just 2D, so it is not that taxing on the compute. If we were to do 3D, it would take much longer. Yeah, let me cancel it. This is enough. Yeah, so here I have, well, actually, let's observe the cell types first. So here I have some cells that I call worker cells. Then I have cargo cells and director cells. So if I go to plot, and maybe I can, yeah. So these are the different cell types. So the worker cells are in yellow, then we have cargo cells and director cells. And yeah, let's just run it. And here you can see that the worker cells are somehow intelligently taking the cargo and putting it towards the director cells. So if I actually click on the substrates, you can see that their movement or logic is actually dependent on the substrate that they are sensing. So first, each of the worker cell goes towards the cargo signal, right? Which is substrated by the cargo cells, and when it is saturated enough with the signal, its internal rules of the worker cell switch, and then they will want to take this cargo, which they got attached to the director signal. So we can see that over time, yeah, maybe let me pause it and move it to the beginning. That all of the director, well, all of the cargo cells were moved to the director cells here. So this is just one way how to use the PhysiCell. So here we are actually using the motility. So if I go to the cell type and motility, we will see that if I switch to the worker cell, that they have enabled the motility with regards to director signal, and also their mechanics are being changed with the attachment rate depending on where in the environment they are. If they are sensing cargo substrate, their attachment rate changes during the simulation according to that. So does anybody need an assistance? Yeah. We can click on the pause. From the run, we can just click on cancel, and then it will stop simulating, and you can visualize everything that has been simulated so far. You can actually also plot while the simulation is running. So let me just click on the run, and while this is going, I can already go to the plot and run play. Perfect. Okay, so now that we are coming to the end of the tutorial, I would like to show you the, let me mirror the screen. The complete PhysiCell tutorial with also the Boolean network extension. So here you can follow this part where we again just create a new or configure a new template project. Well, not template project, but sample project that is already configured in PhysiCell. And yeah, then you can actually read the tutorial, read through the tutorial README. So I just opened one of the configuration file here, and yeah, here we have quite a few cell types. Here we have some endothelial cells, dendritic cells, T0, Treg, Th1, Th17. What is important is that dendritic cell has this intracellular Boolean network, and depending on some signal from the environment, some node of this Boolean network will be triggered, activated. So if I just run the simulation, and give it some time. We can actually observe quite a specific scenario where dendritic cell will want to come towards the endothelial cell, and as it will be touching these T0 cells, they will they will transition their state to Th1, Treg, and Th17. Yeah. And basically all of this is done by the combination of all the parameters that we set. We set the motility of the dendritic cells to come towards endothelial cell, and then we set some rules for the T0 cells to change, to transition to other states depending on the contact with the dendritic cell. We can actually, here we can play with the with the Boolean model of the T0 cell, where we can actually mutate some of the nodes here. And yeah, if I go through the tutorial, you can actually open some of the specific pre-configured differentiation files where some nodes were mutated, so they were knocked out, so that when the T cell comes with a contact with the other cell, it will transition only to a specific cell, not this set of these three different types. Yeah, so through the tinkering with the nodes that you can mutate in the Boolean network, and through the complex rules that you can set up here, like the signals that can be taken from the environment, so that the Boolean network and signaling will be altered, and the different cell will adhere to the different rules, and a different simulation outcome will eventually happen. Here actually, as the dendritic cells are coming towards the endothelial cells, as you can see, their migration bias is less and less pronounced towards the endothelial cells. They will just start to wiggle around the T0 cells, not wanting to go completely towards the endothelial cells. This is also something that we can modulate through the simulation parameters. I have some few of the examples to show, but I think that yeah, I will skip them and just assist you if you have any questions now, or if you are stuck somewhere. Yeah, so just in this case, I loaded another predefined configuration settings where if I go to the cell type of T0 cell, we mutated one node. Well, we suppressed it, and yeah, this node in its own complex pathway actually prohibits the T0 cell to transition to anything else but Treg. So again, some complex scenario that can be simulated with Boolean networks.
John, how do you define the behavior of this T cell or other cell? Is there somewhere we can define it here?
Yeah, I suppose that you can change everything in this part here, in the output part. So here you take a node of the Boolean network, and if this node gets activated, you change the behavior here. There are big set of behaviors that you can actually tune. Well, this just can refer to any parameter of the cell. Here we actually set it to transform to a different cell type. So yeah, that T0 can change to Treg, for example. So yeah, you would do it like this.
Uh, there are already set of behaviors that can be already so this application Visual Studios already prepared a list of behaviors. Can one create a new behaviors something, or should be hard coded in the code of
Yes.
Visual Studio?
So yes, in PhysiCell Studio you have predefined set of signals and behaviors. And if you want to have a new custom one, you cannot do it through PhysiCell Studio. You would need to go through directly to the C++ project file, and there you need to specify the rule programmatically. So yes, in PhysiCell Studio, the authors try to be, as benevolent as possible, try to come with as many ideas the users could be able to simulate. But if you want to do something custom, you need to tap to the C++ code. So I think that I wrote the README in a way that it can be followed along at home at your own pace. If you have although if you have any problems or question, you can ask me now, ask me today, or even write me an email, however you want.
And for those who does not have access to their own local system with all the requirements available, there's a step in WhatsApp that you can still use Fugaku pre-post cluster, and then if I'm not mistaken, you can use the virtual desktop for 30 minutes or probably more, 1 hour, I don't know, probably Chigusa or Georgie knows more. But after that, it will terminate your session. So in order to reuse it, you need to create all the environment again. But yeah, you know already. Yeah, okay. Any more questions? Thank you, Adam, for the